Unit 3 with gravitation, circular motion, orbital mechanics, centripetal force. You get the idea. If I can teach myself 23 AP classes, I can teach you guys much better than your teachers can. Building off a topic that we discussed in the previous video, which is the gravitational force, F sub g. Now, there is an equation on your reference table for the gravitational force that defines it as the magnitude of the gravitational force vector is equal to big G, the gravitational constant, m1 times m2 over r squared. Now, this equation enlightens us to the fact that the gravitational force is a force between two objects with mass. The gravitational force only pulls me down towards the center of the Earth because I have mass. So, let's analyze what this equation is telling us. The gravitational force is equal to the gravitational constant, which is a constant given to you on your reference table. It's going to be in the constant section on the first page, up here towards the top. In the top right-hand corner, you have the universal gravitational constant. Big G equals 6.67 times 10 to the negative 11 times m1, which is one of the masses of our system. Let's just define m1 as being the mass of the planet, also known as the mass of the host. And let's say that m2 equals the object that is in orbit, or the object that is being acted on by the host. For example, this marker would be the object and Earth would be the host. So it would be m1 times m2 over r squared, wherein r is the distance between the two masses, okay? Now, it is important to note here that our distance r is not measured between our markers and the surface of Earth. No, r is the distance between the center of mass of m1 and the center of mass of m2. So the center of mass of Earth is where? It's at the center of the planet, okay? So therefore, our r squared is the distance between the center of the planet and my marker, squared. Using this equation, let us then corroborate what we see in the Newton's second law representation as Fg being equal to mg, okay? Where m is, of course, the mass of the object. If we equate these two, we get mg equals g times the mass of m1 times the mass of m2 over r squared, okay? Where on this side of the equation, this would be mass 2, the mass of the object. I can cancel both of these out and then say that g equals big G times the mass of the planet over r squared. Where remember that our definition of g is the acceleration due to gravity at Earth's surface, or near Earth's surface, which means our r squared would be the radius of Earth. So let's Google a minute. What is the radius of Earth? All right, let's whip out our calculator and use the gravitational force equation to verify Newton's second law. Let's take 6.67 times 10 raised to the 11 times 5.572 times 10 raised to the 24, and I'm going to divide all that by 6.371 times 10 to the 6 squared. And we're going to get, you guessed it, 9.81. Therefore, G equals 9.81. This is a symbol I will very often use in my videos. The 3 dots in a triangle. It means therefore in physics and math, etc. I use this on my AP exams. It's a lot quicker than writing the word therefore. And why does G not vary with respect to radius? Well, G does vary with respect to radius, but like I said previously, the radius of Earth is over 6 million meters, okay? So if I raise my marker up by another 100 meters, 100 meters is absolutely insignificant compared to 6 million meters. So 100 meters plus 6 million meters is approximately 6 million meters. Therefore, the value of G does not change if you only consider the first 2 decimal places. It doesn't change, assuming you do not go significant distances away from Earth. Once you surpass maybe 1,000, 10,000 meters, then G will start to change. So a very common problem type you will see with respect to this unit is, hey, we've got a different planet, let's say Mars, and Mars has a different radius than Earth, and Mars has a different mass than Earth. So I want you to calculate the acceleration due to gravity on Mars, okay? So in our equation right here, we deduced that the acceleration due to gravity, g, on a planet is equal to big G times the mass of the planet over the radius of that planet squared. If the problem asks you for g near the surface of Mars, it's going to give you the mass of Mars and the radius of Mars, and then you just plug and play. Moving on from there, with gravitational force, the main principle that we're going to be looking at here in the gravitational force unit is circular motion. Why is circular motion related to this? Because orbit. When you put a satellite in orbit, it undergoes uniform circular motion around Earth. So let's draw a diagram of circular motion. Obviously, circular motion stipulates that you would be moving in a circle. And every circle has a center, which means your circular motion can be defined using the center and the radius outside of which you rotate. You'll notice in physics that the letter D and the letter R are used interchangeably to represent distance. In this case, R is representing the distance from the center. So what do we mean when we say uniform circular motion? Uniform circular motion means that you are moving in a circle at a constant velocity, okay? In stark contrast, you have just normal circular motion at which your velocity may or may not be constant. But what's important to note about uniform circular motion is there's a little nuance to it. If in uniform circular motion, your velocity is constant, is a force acting on you. Many people would get tripped up and say, no, if velocity is constant, then there's no net force. But that's incorrect, because velocity is a vector. Okay, let's discuss the importance of that. In uniform circular motion, the magnitude of the velocity vector is constant, meaning you are still moving in the same speed, but since you're moving in a circle, you are not moving in the same direction, okay? The magnitude of the vector, the value of your velocity is constant, but the direction in which you're moving is changing. So since velocity is a vector, and the direction of that vector is changing, it means you do have a net acceleration, okay? If I am moving in a straight line this way, I need a force to come and act on me if I want to start moving that way. You see? So the force that is acting on you to consistently change your velocity is called the centripetal force. The centripetal force constantly points towards the center. Okay? Now, many of you think of the centripetal force as, oh, my car is about to go around a turn, and because it's about to go around the turn, I am going to feel smushed up against my window if I'm on the opposing end of the car. If I turn this way, I'm going to feel smushed up against my window like this. The centripetal force in that case is the normal force of your car door acting on your body. And which way is that normal force pointing? It's pointing, first of all, perpendicular to the plane of your car door, and second of all, the plane of your car door is now going to be pointing towards the center of your rotation. Let's draw an example of that. If you're going around a bend like that in your car, like this, the center of your rotation would be right here. You would be forced up against your car door like that. The car door would be exerting a normal force onto you, which is what you feel when you touch something. And that normal force will be directed towards the center of rotation. Because if I have a vector that is moving directly this way, and I want it to start to curve that way, which way do I need to apply a force? I need to apply a force exactly perpendicular to it. And that constant application of force, the constant application of a force that is perpendicular to velocity, is how you move in a circular path without changing the magnitude of your velocity. How do we quantify the centripetal force? The centripetal force, like I said, is the force that pulls you towards the center, the force that allows you to engage in circular motion. If I am having these rosary beads move in uniform circular motion, the force, the centripetal force that is constantly altering the direction of velocity, is going to be the tension force in the string. Okay? That's the force that is acting on the edge of the rosary beads in order to change their velocity and continue altering the vector to move in a circle. Okay? If I were to suddenly cut off the centripetal force, remember the centripetal force is the force of tension in the string. If I were to suddenly cut the string, that would suddenly dispel the centripetal force. What would happen if I cut the string? That means that the edge of the rosary beads would continue to move in the velocity vector that they were moving at the instant the string was cut. Okay? Because the force is not changing the magnitude of the velocity, only its direction. So if there is no longer a force changing the direction, then the direction stops changing. And the edge would continue on in exactly the vector that it was spinning at the instant the string was cut. Tension force, F sub t, is equal to our centripetal force, F sub c. Now, on your equation sheet, you have an equation that governs centripetal force, but more specifically, it governs centripetal acceleration. Towards the middle of the equation sheet now, we're moving down the equation sheet slowly but surely. Well, not really the middle, it's going to be the sixth equation. It states that a sub c equals v squared over r, right? Yeah. A sub c being centripetal acceleration. By Newton's second law, the centripetal force equals your mass times your centripetal acceleration. Therefore, your centripetal force equals your mass times v squared over r. M being the mass of your object, v squared being the velocity of your object, the linear velocity, and r being the radius or distance which your car or object is revolving around the center of rotation. So, therefore, if we were to spin around the center of rotation at a greater velocity, that would require us to have a greater centripetal force, okay? If I decrease the radius while maintaining the velocity constant, I would need to increase my centripetal force, okay? And since the centripetal force is equivalent to the tension in our string, that means that the faster I spin the string, the more centripetal force is required to keep the string in uniform circular motion. And if I keep spinning it faster and faster and faster and faster, the required centripetal force will continue to increase until the centripetal force exceeds the tension force that the string can supply and the string breaks. That principle is the principle that is used to govern orbits. Okay? We've got the sun at the center, and we've got Earth. Now, a little bit of a tangent right here. If you were not in uniform circular motion, let's say you were moving in circular motion and you were speeding up, that means that you would have a force, a centripetal force, pulling you towards the center, and if you were speeding up, you would have an applied force that is acting in the same direction as your velocity vector. Consequently, if you were slowing down in circular motion, you would have your velocity vector, your centripetal force vector, and the applied force would be acting against your velocity to slow you down. Let's examine the uniform circular motion of the Earth around the Sun. If the Earth is entering into circular motion around the Sun, what is our centripetal force? What force could be pulling the Earth towards the Sun that we could use to supplement our analysis? What force exists in space that pulls the Earth towards the sun? Gravity. So this is going to be a process that you need to go through every time you enter into a problem with uniform circular motion. You need to deduce in your head what could be acting as the centripetal force in this scenario. If we return to the car example, where your car is making a right-hand turn, the centripetal force that is forcing your car towards the center is the friction of your car tires against the road. Okay? The friction of your car tires against the road, which would be static friction, well, I'll explain that more in the rotation unit. The friction between your car tires and the road is being engaged in the direction towards the center of rotation. In this case, the centripetal force would be your gravitational force. So remember, our centripetal acceleration equals v squared over r, taken from our reference table. Therefore, by that token, the centripetal force equals the mass times v squared over r. Now again, since we're dealing with orbital mechanics, we need to specify which mass this is. This would be mass 2, the mass of our object. Now let's write the force of gravity equation. And since we know that the force of gravity is our centripetal force, Fg equals Fc, we can therefore write that G m1 m2 over r squared equals m2 v squared over r. Okay? m2 exists on both sides of the equation. It cancels out. Let's rewrite this as G m1 being the mass of the planet over radius squared equals velocity squared over radius. We got radius on both sides. Big G, mass of the host, over r equals v squared. What is v squared in this scenario? V squared is the velocity at which we orbit. Therefore, our orbital velocity v can be given by the equation rad big G m1 over r. You will often be asked to illustrate the free body diagram of a species or body existing in circular motion. Okay? So like we have demonstrated up here, your free body diagram, you would, let's say that this is your center of rotation, this C, letter C. Your centripetal force on the free body diagram would be directed inward towards that C, and that would be the only force acting on you if you are in uniform circular motion. If you are accelerating or decelerating in the path, then if we have a velocity vector this way, meaning you're at that instant moving in this direction, then your acceleration would be in this direction. An applied force would be applied in that direction if you're accelerating. You would have an applied force going contrary to your acceleration vector if you're decelerating. Let's examine how your mass affects your orbital velocity. Okay? A very common question is, if I have a satellite orbiting around the Earth, let's draw a second representation to take a look at that example. If my center is Earth and I have a satellite orbiting around it over here, and I have a second satellite orbiting over here, let's call this S2 and this S1. Let's say that S1 has a mass of m and S2 has a mass of 2m. My question to you is, which one orbits around the Earth faster? Notice how they are in the same orbital radius, meaning they orbit in the same path. So we are making the deduction that therefore r is equal for the two satellites. Trick question. Looking at the equation we just derived here, the orbital velocity of any body is determined by their radius from the host and by m1. What's m1 again? It's the mass of the host. Therefore, m2, the mass of the object, has no place in determining orbital velocity. So we can say that orbital velocity is not proportional to m2, mass of host. Sorry, not mass of host, mass of object, excuse me. But what can alter orbital velocity? Orbital velocity is affected by the distance from the host. So if instead S2 is placed on a more further out orbital path, and S2 were right there, then we would have a greater radius, which means the orbital velocity has decreased. What if we operate at a different planet that has a greater mass than Earth? In that case, your orbital velocity will have increased. So gravitational acceleration, orbital mechanics, centripetal motion, uniform circular motion, this is all not a lot of new material. It's more of applying skills. It's more of learning how to derive equations. It's more of trying to deduce which of the forces acting on an object are the centripetal force. It's determining how varying different factors can affect different quantities. Like how does velocity behave when you vary the radius? How does velocity behave when you vary m2? So it's largely a unit devoted to you practicing your skills, which, as you can see here, it's a much more math-dependent unit. Thank you guys so much for watching. I look forward to seeing you Unit 4.